Very good afternoon. So good to be back at conferences after a long time. We missed you all, and great to be speaking to you today. We go to conferences a lot to share insights from our research and from our consulting work in security. Today we do a bit of both on a very relevant topic, which is evading EDR. EDR stands for endpoint detection and response. It's basically your modern antivirus that should keep you safe from malware, but we'll show you today that it really doesn't, or contribute a little bit, but definitely is not a cure-all for the malware problem. We have a bit of background on how EDRs generally work. We'll then explain how to get around the protection measures, and we'll discuss a little bit at the end what additional controls you would need to actually be safe from malware, if that's even possible. This should be interesting for you if you have not heard of EDRs before, obviously. A lot of the techniques, though, that we cover are well documented in other places. We didn't reinvent the wheel here. EDR evasion is a popular technique among red teamers. So if you haven't been exposed to the topic yet, this is a great place to start. But if you do know a lot about EDRs already, I think we brought an overview that you would not have seen anywhere else. Which evasion techniques work against which solutions, exactly what you should be focusing on to have a very effective EDR evasion setup. Right? With that said, why are we talking to you about this? Here with my colleague Jorge, who's a red teamer. We both work in Berlin at SR Labs. And as part of the red team activities, of course, we have to break into companies and basically in a multi-week or sometimes multi-month journey, take over the entire company. That's the job of a red teamer. And more often than not, of course, we encounter an EDR in the process. I'm Karsten. I'm not doing red teaming so much. I'm more focusing on other critical infrastructure, telcos and whatnot. But then increasingly too, we encounter EDR systems and similar. So EDR evasion just belongs into the toolbox of a versatile hacker these days. Which is why we are running our own small EDR test lab. We have to. So for instance, when we encounter a new EDR during a red team engagement, instead of trying out our samples in that environment, we run it in our own test lab until we're reasonably sure that it's not going to trigger any alerts. So you need that test lab environment. And it's set up probably exactly how you would expect. There's all kinds of virtual machines running that you have different EDRs or the same EDR in different configuration running, and then we put the same malware vectors into all of them and see which ones trigger, which ones don't, until finally we find samples that none of them detect anymore, and those are then good to go for a red teaming engagement. All right, so I'll cover the background, and then Jorge is going to give you the more interesting results. So let's start with how EDR systems in general work. They combine three analysis techniques, two of which you already know from antivirus, and the third one is really what makes EDRs different from antivirus. So the two known from antivirus is static analysis, where basically you just look at a file, and just from looking at the file, you have to decide, is it a virus or not? Dynamic analysis runs the file, but often in a sandbox environment or some kind of a virtual machine, and then decides based on the behavior in that virtual machine, whether it's malicious or not. And behavioral analysis, the part that is new for EDRs, that runs the potential virus on your actual computer, and observes it, and then has to decide pretty quickly, is it a virus or not? Because you already started it, right? So you have to quickly kill it if you think it's malicious, right? So let's zoom into each of those a little bit more. Static analysis, right? That's probably easiest to explain. You take any kind of executable, and when it's downloaded or at the time that it's about to be executed, you parse it for all kinds of information. Could be, for instance, IP addresses, could be hashes, all kinds of information that you might have seen in other malware samples, right? If you're communicating, for instance, with the same command and control infrastructure. So then you learn, okay, this is another copy of that same virus I knew before. This is how antivirus used to work. You basically infer from all the viruses that you have seen in the past, that this, again, is a new virus. This is pretty simple to circumvent. by obfuscating or even encrypting all that interesting information. So basically, you take the virus, you encrypt it, so that in the file itself, there are no IP addresses or known hashes anymore. And then basically the only part that could be detected is, of course, your decryption routine at the very beginning of the file. So as long as you obfuscate that enough, you're usually safe from static analysis. So this is mostly an outdated analysis technique. Of course, they still throw it in the back. More helps more, of course. So modern engines run this kind of in parallel to the other stuff. So let's come to the second one, dynamic analysis. Again, this is when you take your potentially malicious binary and you run it, but you run it in a shielded environment, referred to as a sandbox. Now, this time, the malware will actually start decrypting itself. So it will disclose things like IP addresses, for instance, by way of opening network connections. So again, you're basically looking for those known bad indicators of compromise, like IP addresses. But this time, the malware doesn't have a way of hiding it anymore. It has to communicate with the IP address, of course, right? You can also look for malicious behavior. Say the malware were to create a user or start reading some process memory, else's, for instance, right? So these are very suspicious things that usually only viruses do. So based on that only, you can then decide, this is a virus, I'm going to delete this, this cannot run on the actual system, right? And this, in theory, is actually a very powerful technique, because if your list of malicious behavior includes everything that the virus would possibly want to do, you're constraining it to basically be useless. The way viruses get around this, though, is by detecting the sandbox itself. So at the very beginning, the virus will check, is this a normal computer that I'm running, or is this a sandbox? And if it's a sandbox, it's just not going to do anything malicious. Right? So how do you know that you're running in a sandbox? There are certain generic characteristics. It usually has just one CPU. It has a limited amount of memory. But there's also pretty specific things that you can code into your virus. So imagine you're sending viruses to specific people, right? And you want exactly that person to open that copy of the virus. You can check from the virus binary whether the user account exists, right? Does that user account exist on Windows? And if it doesn't, that indicates that it's running on some kind of other machine. Could be the sandbox. So you just don't do anything malicious, right? So there's many ways to avoid being sandboxed and detected that way, which is then why the EDR solutions introduced this third analysis technique, and that's called behavioral analysis. So this time you run the malware again, but not in a sandbox, but on a real computer. And you check on it very closely to see what it's doing. And the way this works, I have to give you a little bit more context. So whenever any process starts, well, typically, could be malware, could be anything else, it loads certain libraries. Those libraries are used to interact with the operating system, right? It's just too messy to interact with the operating system kernel directly, so you use those libraries as kind of a buffer, right? As soon as those libraries are loaded into the process memory, the EDR, in green here, will overwrite parts of these libraries to hook itself into it. So the malware calls the library. The library is now supposed to call the kernel, but instead calls the EDR instead, gives it some information and basically asks for permission to proceed, right? So at different points during the execution, the EDR learns information about this process and each time can decide this is malicious or this is not malicious, right? So look at this from the perspective of the malware, for instance. As we said at the beginning, it usually keeps all the interesting stuff encrypted so that the static analysis doesn't work. So what's the first thing the malware does? It has to allocate some new memory. It has to decrypt its payload into that memory and then execute that new code from that new memory, right? So allocate, copy into, and then execute. Those three steps in that order are almost always a virus, right? And the EDR through these hooks learns that exactly these three things happen in that order, and it will stop the malware basically a millisecond before it was about to execute. In that third step, it says, no, if those things happen in this order, malicious, stop, right? So it's playing with fire a little bit, right? You get very close to malware executing, right? So that's what we're up against when we in our EDR test lab have to circumvent EDRs now. And I'll just very briefly go over the techniques in one overview, and then Jorge is going to fill in all the details. So what we're going to look at next are basically different ways of evading this behavioral detection. All of those start by or we're prepared to evade static analysis and dynamic analysis. That goes without saying. We don't want to make it too easy for those solutions. And then we're playing around with these different ways of getting around the behavioral analysis part. We have some samples that don't try this at all, kind of as a reference case, right? That they run as if they're up against an antivirus solution, say. And then there are 3 actual evasion techniques. And just in a nutshell, what they do is the first evasion technique overrides again what the EDR had overwritten, so basically restores the original system library so that these hooks go away. The second evasion technique attacks directly with the kernel, so basically going around the overwritten system library. And the third technique, this is the most interesting, uses just very small code fragments, basically single instructions from the libraries, and by just using those instructions, they don't trigger the hooks. Again, Jorge knows a lot more about this, so over to him.
Yeah. Yeah, it works. So yeah, as we have mentioned, EDR is going to place its hooks inside NTDLL. That means that it's going to modify NTDLL in the memory of our process to analyze our behavior and see what we are actually doing. So the first thing you can think about, and the first technique that comes to your mind, is that you want to remove those hooks. You want to restore the original NTDLL before the EDR has ever interacted with it. To do this, we need to overwrite our NTDLL in memory. And that means that there was a time in which NTDLL was unmodified, and there has to be a fresh copy of NTDLL around our Windows system that doesn't contain these EDR hooks, because it is designed to be that way. Windows needs to work with these fresh NTDLLs, and they have to be there. They are only modified once the EDR is loaded in our process. To obtain a fresh copy of NTDLL, we can approach different ways, right? The first way would be read NTDLL directly from disk. We know that NTDLL was unmodified before the EDR modified it in memory. So if we just go to the original location and map it in our process and overwrite then the overwritten NTDLL, then we'll get a copy of NTDLL will be in our process without being modified, without any hooks. Another approach to this same problem was disclosed by the folks of Sector 7 and involves starting a process in a suspended state and copying NTDLL from there before the EDR has placed its hooks in the new suspended process. This is because the EDR is only placing its hooks in a certain moment of the execution. With both approach, we are going to obtain the same results. And as long as we can obtain a fresh copy of NTDLL, we should be good to go. Our objective is the same. So we can really get creative. There are a lot of ways of actually obtaining the same objective. No matter how we do it, we just need to obtain a fresh copy of NTDLL and overwrite our in-memory NTDLL. In this case, ideally, the EDR would see nothing, but obviously there are different hook implementations and the EDR sometimes plays hooks in another way. For the purpose of this talk, we are only talking about hooking techniques that focus on NTDLL. Also, we came across a problem when we are doing this technique. The first thing we face is that accessing NTDLL is a quite common flag activity. And that's because basically every threat actor was doing that to remove the NTDLL hooks, because it's basically what the first thing you think about when you want to override your NTDLL. And also the second thing we face is that the API calls we are actually using to override NTDLL are also hooked. So it's a bit uncomfortable because the EDR is actually seeing what we are doing in the meantime. So it's like the EDR knows that you are trying to remove the things that allow him to see you. So probably you are going to also get killed if you go this way. So to overcome this problem, let's go and face a different approach. And in this case, we are going to talk about one technique that does it in a completely different way. In this case, we are avoiding removing the hooks from our process, but instead we are going to interact with the kernel directly without going through NTDLL. This technique is called direct system calls, and it has been pretty much used for the last year in almost every loader out there. What we do in this technique is that basically we implement our own system calls directly in Nohl malware. To implement these syscalls, we need one parameter that is called system service number. The SSN is a simple parameter that allows us to identify which system call we are using. In this case, you can see that number 18 refers to NT-allocate virtual memory. The problem we face also with this approach is that obviously this system service number varies from Windows version to Windows version. That means that if we want to target a certain, if we know the target we are targeting and we know exactly the system version we are targeting, we could hardcode the system service number. But that's never the case, obviously. You never know what you are targeting. To avoid this, you can also obtain this number dynamically, inferring it from the functions of NTDLL that are not hooked. We are not going to go too deep into this because it will be much harder to understand, but there's a lot of work on the area, and if you can check SysWhispers too, who have made easy to weaponize this technique. The second thing we need is basically the syscall instruction. It's a syscall instruction that is going to change our context and interact directly with the kernel. Once we have specified the correct system service number. And here again, we see another problem. As you can see, there shouldn't be any problem because we are interacting directly with NT-allocate virtual memory without going through the EDR hook. But because we are using the syscall instruction directly in our malware, we might get flagged in static analysis. If you think about it, I can think of non-malicious software that performs system calls directly without going through NTDLL. So that's a no-go, and that's an OPSEC-friendly thing to do. And the EDR might flag this statically by just including the word syscall, the assembly instruction. And also, one thing we need to notice is that we are creating a loader and injecting our payload in a thread, but the problem is that we are not unhooking our process. And that means that only the loader is evading the EDR, but everything we do after that is subject to analysis by the EDR. So if the command and control is interacting, for example, with the system and is doing some API calls, those are also going to be analyzed. So you need to be really careful once you have injected successfully in a process. To avoid the first problem, the problem in which we specify exactly the syscall instruction in our assembly code, we can use a technique that we can call indirect system calls. Really, it's a different approach to the same technique we saw before. In indirect system calls, we are also going to still specify the same assembly instruction in our code. You can also get this system service number dynamically, but instead of actually calling syscall, what we are going to do is that we are going to take a different direction. We are going to jump to one syscall instruction we can find inside NTDLL. That way, what we accomplish is that we are not calling syscall directly from our malware, which is quite suspicious, but we are calling syscall directly from NTDLL, which avoids being detected by the EDR in static analysis, and also is way more OPSEC friendly, because the instruction is being called from NTDLL after the hooks are placed. And that's how it's supposed to be. These syscalls should be called from NTDLL, because that's how Windows is designed to work. Now, before going to the actual results, let's discuss a bit some things about Windows for those who are not used to it. We are going to see basically two different formats. Before continuing, obviously, the best technique you can use would be to combine both, right? To combine indirect system calls and unhooking to create a perfect loader that doesn't have hooks in place and that can inject without actually the EDR noticing. But as that's pretty complex and you can infer that from the context of this talk, that won't be included here. And just, again, let's go back to here. We are going to see two different formats. The first format is .exe, which is the normal binary format you can expect. It is the binary that you can think about, that you just download and execute. Because of this, it is designed to be run independently. It's designed to be run. And also, because of this, has its own memory space. It's inside the process and is contained inside. the nature of this type of binary makes the EDR way more suspicious because it is designed to be run independently. So the EDR is more likely going to inspect these files much more closer compared to DLLs. Instead, with DLLs, we have the Windows implementation of Linux share libraries. These DLLs need a host process to be loaded in, so they cannot be run independently. And because of this reason, they don't have its own memory space. They share the memory space with the host process. So for the EDR, it's way harder to detect what is actually happening because the malicious actions are coming from a non-malicious process. Now Karsten is going to show with you some results of our test lab and what happened in our test lab.
Good stuff. So 3 different techniques to evade this behavior analysis. Here now the results from our test lab. There's a lot of stuff packed on this slide, so let me unpack that for you. Maybe let's start on the left side. There's these 5 different test cases basically. The first 2 don't try to evade anything about the behavior analysis. In fact, the first one doesn't even try to detect the sandbox, right? So it's really a base case that technically, even an antivirus system should have picked up. The antivirus system that we ran for reference did not pick this up, surprisingly. But of course, the EDRs did. The next case then avoided the sandbox using the techniques we showed earlier, basically figuring out I'm running in a sandbox, hence I'm not going to do anything malicious. And then these 3 build up on that sandbox evasion with the 3 techniques that Jorge has explained, right? And then we run this for these 2 cases with the XC and the DLL as just motivated. Right? Again, a lot to unpack here. On the right-hand side, you see the antivirus didn't see anything. So some initial evidence that EDRs are not useless, right? That's good. But also there's too much red here to conclude that they're the cure-all. Let's zoom into a few places. Okay, I explained how hiding inside the DLL might be advantageous to basically confuse the EDR. The EDR will remember, oh, this is an exe file that somebody downloaded, now they clicked on it, now it's executing. It will observe this very carefully. Whereas with the DLL is put somewhere in the file system, and then the EDR kind of forgets about it. And at some point, something completely different will launch and load this DLL, so it's checked much less carefully, so it appears. And we'll have a demo in a few minutes to show how exactly this side loading or hijacking of DLLs works. The clear evidence that DLLs are better than executables. Next one, Cobalt Strike and Sliver are 2 standard tools to use, basically hacking tools to use for command and control and to basically abuse the system after infection. Cobalt Strike is much more popular than Sliver, or in much more popular use. So it appears that the EDRs focus on exactly Cobalt Strike behavior. Rather than detecting malware in general, they're trying to detect specifically Cobalt Strike. Right? At least that's what these results seem to suggest, right? And that's in line with our experience, where in our test lab we try to avoid the most popular hacking tools because those tend to be flagged more. And then you go to something less popular, to Sliver, or in our case, even to something completely custom. If you want to be extra sure that you're not triggering something more signature-based on Cobalt Strike or a tool like this, but that you could only really trigger the behavioral part of the analysis. Next, or finally, I should say, we see that there are some evasion techniques that work universally. So you don't need to prepare your evasion for one specific EDR solution. These latter 2 techniques, direct syscalls and indirect syscalls. In our lab, we're able to circumvent every single solution. And you saw it on the slides earlier. These solutions are representative of kind of different parts of the market. We're not going to tell you which is which because we, of course, don't want to put blame on one specific vendor, but showing kind of ecosystem-wide issues. But the ones that we did list earlier, there's, of course, kind of the default go-to option, Microsoft Defender for Endpoint, which a lot of companies have as part of their Microsoft subscriptions. Then we tested one that grew out of an antivirus company, Symantec EDR. They were a little bit late to the game, but they have an EDR product too now. And then there was one that's kind of an original EDR, Sentinel-1. right? And these three kind of represent the whole spectrum of the market as far as we can tell. And all of them were evaded using the very same techniques. But that's only half of the story. So far in the story, we have started executing a malicious program without the EDR saying, no, you're not allowed to execute. So we're running code on the machine now. But that code hasn't done anything yet, right? So it hasn't copied any files, it hasn't created any user account, none of that stuff. So next we're going to look at whether the EDRs have a chance of detecting it after it starts doing malicious stuff, because you would imagine the EDR has a lot of heuristics about the behavior after executing as well. And again, pretty disappointing results.
So yeah, as we discussed, now we are going to mention what we do once we have successfully injected in a process, and once we have a command and control connection, and we can interact with the victim computer. Let's separate this example in two different things. The first things are the core functionality of our command and controls of both Cobalt and Sliver, and the second part will be community extensions, things that the community can build to make our tools better. If we look at the core functionality, for example, we can see certain things like basically all of the stuff you can see here are stuff that we need to conduct our red team engagements. Are things without those would be much harder to conduct our engagements. The first thing, for example, will be open a SOX tunnel, which allows you, once you have compromised a system computer, to pivotate through the network and to access those Apache Tomcat servers with default passwords, and those legacy servers that you can find in organizations, in huge organizations. Also, we can see data exfiltration. That's a typical approach we can see for downloading a document from the computer, or even like exfiltrate some data from there to show some proof. Both were completely undetected in all of the tests we did in all three EDRs. Also, we can see some detection starting with keylogging, but only in one EDR, and it was Cobalt Strike. So we think that this was mainly based on fingerprinting on how Cobalt Strike performs keylogging, and not but the keylogging activity itself. If we go to the last core functionality that we usually use in our red team engagement, we see execute assembly. And this starts being one of the capabilities that allow us to improve our command and control and add new capabilities. In execute assembly, what we are doing basically is executing C# binaries inside a process. In this case, both Cobalt Strike and Sliver use a technique called fork and run, which basically creates a new process and executes the binary directly in the memory of that process. Surprisingly, and because it has been quite abused for the past years, it was detected in Cobalt Strike in all three EDRs and only once in Sliver. But still, any technique based on fork and run is definitely a no-go, because in the new process, the EDR, the process is completely hooked, and the analysis is quite heavy on that. Also, we can avoid using execute assembly at all, because we can use, for example, beacon object files, which are basically applications built by the community that allow us to enhance Cobalt Strike and execute inside the same process, inside the same beacon. We ran some tools at Sharphound, which is a pretty well-known tool to enumerate Active Directory, and that was completely undetected. Also, another BOF, another beacon object file you can use is inline execute assembly, which mimics the results from execute assembly, but executes that in the same process without doing fork and run. And surprisingly for us, this technique was completely undetected in all three EDRs. So we can still have the execute assembly behavior without actually being detected. The things we can take from here is that obviously Cobalt Strike is the most detected command and control out there, because basically every EDR is working against Cobalt Strike. But if you use other EDR, if you use other command and control, you are most likely it will be easier for you to be undetected. Also, we can see that all the detections we found were basically on the core functionality of both command and controls, which means that as long as we start building new capabilities or modifying the in-house capabilities, we are going to be much harder to detect. The EDRs are having a really hard time detecting our actions dynamically. But we have talked about only one part of the picture, right? because we have talked about how to build these payloads, how to build our binary to drop it into a server. But the EDR is not only looking at that. The EDR is looking at everything that happens before and after the execution. So let's see a full end-to-end kill chain to show you some of the things that we did in our engagements to actually bypass a real EDR. The first thing, in this case, I'm going to show you some bypasses we need to do in order to accomplish this. Obviously, this is not part of the talk by itself, but they are easy to understand, and I think you will see the demo better if I explain this. The first thing we are going to do is to create a link file, a shortcut basically, that points to a Microsoft application, points to a binary that is on the file system. But the problem we need is that we want the user to download this file, but unfortunately we cannot do it through a browser. So to bypass this protection, what we are going to do is basically compress this file into a zip file, and then we are good to go. The second stuff we are going to face is app locker, which is a really common protections in Windows environments that prevent us from running certain binaries. In this case, what we are doing to overcome this is making this shortcut that the user is downloading point to MSHTA, which is a common binary that you can find inside Windows. MSHTA also allows us to download HTA files, which are HTML applications, from a remote server and execute them. So actually, when the user clicks on the shortcut, it's going to download a payload from our server and executes the first stage, our dropper. This is not going to be malicious at all. What it's going to do is only going to open a PDF document and then download our real DLL or real malware into the Teams folder. And there, due to DLL hijacking and due to the fact that Teams is looking for one concrete DLL, the malware is going to be executed every time the user opens Microsoft Teams. But I think this would be way easier seen if I show you a demo. In this case, I receive an email, and I just open the email and open the link because I have an EDR system that is obviously really advanced and it's going to protect me against everything that happens to me. So it says that it's legit, so I download it. Takes a bit. And as you can see, it's again, as I mentioned, zip file. So I open the zip file, and here inside, you can see, you can see that it looks like a PDF. It doesn't have a link extension, but if you look closely, it says that it's a type shortcut. And when we unzip it, you can see also that it looks like a PDF. It has an icon of an actual PDF, so the user can be tricked into thinking that this actually is a PDF. Okay, now we open the PDF, we open the link file, and, oh my god, sorry.
Just stay inside the window,
We open the PDF file, and we can see that on the Teams folder, there's no DLL file. We open the link file, and it shows us a real PDF. In this case, there's nothing harmful here. What we are doing is completely okay. But in the background, a DLL has been downloaded that basically is going to allow us to get execution. Now let's see what happens if we open Microsoft Teams. As you can see, we have received a session, and we have now full control of that computer. That computer is running a full EDR and every evasion system activated. So now let's see what we can do to interact with this system. We can conduct anything that I talk about on the dynamic behavior. We can, for example, list files, and you'll see that we are inside the Teams folder as expected. We can even enumerate different processes and see what is inside the computer, what other system or defensive measures we are facing. And finally, we can do something that is not really useful for red team engagements, but it's quite scary, and it's taking screenshots. In this case, we are taking one screenshot. I'm going to move the PDF a bit to show you that it's really a screenshot of the moment. It's going to take a bit. Okay, there you go. And now you'll see that we have the same screenshots I showed you before. And then we have fully compromised a computer that has an EDR system in place. The key to this, and the lesson we can learn from this, is that the best way of actually evading an EDR is detaching the execution from the download. As you can see, our first stage have done nothing malicious. It just downloads a PDF document, opens a PDF document, and downloads a file into a random folder. But actually, the EDR doesn't correlate those two events and doesn't think that our actual downloaded file is conducting anything bad, because indeed it's not doing anything bad. So the key to evade EDRs is to detach these two things, the execution and the download, and keep them as long as possible, and separate them as much as possible to make the EDR doesn't correlate those two events.
All right. Yeah, very nice. So again, this was executing a malware, in evasion of the browser security features, the Microsoft built-in Windows security features, and the EDR on a fully patched, I guess this is Windows 10 machine. So where does this leave us? What is the protection level now that we can expect from a fully featured EDR? Well, let's first ask a slightly different question. Do we even need EDRs on endpoints? Because there is an alternative, and I should add one more piece of information of how we configure the EDRs in our test lab. We switch on every single feature that they have. We make it as difficult for us as possible, except for one feature. We don't allow them to send the executable to the cloud, have some kind of cloud analysis done, and then use the results. Because that, again, is sandbox analysis. That's not behavioral analysis. And also, we are more interested in what happens on the endpoint. Can you detect malware on the endpoint? Yes or no? That's what the EDR started to do. But we wanted to add that bit of information. What happens if you do upload it to the cloud? Not to that specific EDR vendor's cloud, but to the more generic cloud, VirusTotal. They run about 70 antivirus engines, or I guess EDR engines, but without behavioral analysis, obviously, right? They don't have access to your endpoint. And those samples that were able to evade every single EDR solution, they are detected by about a quarter of the engines running in VirusTotal. So not all hope is lost. But interestingly, this is the older technique, right? This is dynamic analysis, running something in a sandbox and trying to decide whether it's malware or not. I should say that some of these could be actually, what is then, false positive. So they detect that it's a malware, but they're detected for the wrong reasons, right? So they might have falsely triggered on something else. But we can be reasonably sure that not all of them are false positives. Do you guys need to do something to bring this back? Wake up. Yeah, so we upload this to VirusTotal, and it does get detected. While on the endpoint itself, where you should be able to do much deeper analysis, it does not get detected, right? So perhaps the answer to malware isn't more analysis on the endpoint, but just more analysis of stuff that is ingested into the organization before it hits the endpoint, right? Most malware comes through something cloudy, right? Some websites, emails, for instance, chat messages, right? So why not run it through something in the pipeline there? Yeah, I can continue with just audio track, but it would be nice to have the picture back. So coming back to that question, do we need EDRs on endpoints at all? In our experience, actually, yes. Not because they are 100% keeping you 100% safe, but because they are making the hacking journey somewhat more complex. So let's use a kind of an average example here. When we are asked to break into a large corporation and take over the entire company, basically from Active Directory down, it takes us, including preparation, about 8 weeks. Okay, so full-fledged red team engagement, 4 people, 8 weeks. It's a lot of work, but there's, of course, a lot of ground to cover also in those organizations, right? So, if at any point we encounter an EDR in such a hacking journey, we know, okay, this is a lot of additional work for us. Typically, of those 4 people, one of them, of Jorge, will be assigned, you take care of the EDR. Whenever we plan an action, you tell us whether you think the EDR would be suspicious of that and advise us how we can be more careful. He'll prepare all the evasion techniques, everything. So about, let's say, half of your time will go on just the EDR track. So, it was 8 weeks before. If half a person is busy half of the time, now it became 9 weeks already. So to just give you the roughest rough estimate, that I've probably ever done, it will add these 12%, of hacking time, to an EDR journey. Should we try this adapter?
That was meant to work.
It's not detecting any monitor, otherwise it would change its resolution.
No,
I don't think it's on this side. This was fine before. I think it's somewhere in your chain further down. Oh, now it found something. So if a typical red team journey is 8 weeks and the EDR adds 1 more week, that's 12% more. Doesn't sound like a lot, but if every single security control you had added 12%, that's pretty good. You have what, like 50 security controls in a big organization? So not every control adds that much. Hence, EDRs, as much as we criticize them today, are among the best one thing you can do. But they're not enough. They need to play in concert with a lot of other controls to always add a few percent and a few percent until eventually it's so effortful to hack an organization that a hacker will just give up and go somewhere easier, right? So what are other ideas? What are other controls that you think will slow down hackers? Any ideas? What do red teamers really hate? How about application allow listing, right? So if you have a list of all the programs you run, and you say only those programs are allowed to run in an environment, it's very difficult to install malware. You have to resort to what's referred to as living off the land technique. So basically using stuff that's already installed and allowed. And the more you lock down an endpoint, the more difficult that becomes, right? So that's probably about as effective as an EDR. It doesn't cost an excessive license fee like some of these EDR solutions, so it might be more bang for the buck, but it puts more burden on you as the organization rather than leaving it all to the EDR vendor. So that's definitely, that needs to be part of the concept. As we said earlier, you should heavily monitor everything that's ingested into your organization. It used to be mostly Office files, Office macros. Microsoft has put a stop to that recently. So now, basically overnight, all the hackers have switched to link files, like that technique that Jorge has shown you today. But what's the last time that you received a link file from anybody outside of your organization? Right? That never happens. So why are they even making it through email gateways, even when put into a zip file? Just do not permit link files to be ingested in your organization. Again, you are adding a few percentage points to the hacking effort, right? What are other ideas? You guys tell me. Anybody working at a company that doesn't want to get hacked? Anything in the area of zero trust, or what Microsoft often refers to as tier zero model. So basically the idea of segregating privileged users from non-privileged users. That's super powerful in slowing down red teamers. Basically, the idea is that if I take over a user endpoint, I can put as much malware on there as I want, because that user endpoint will never be exposed to user accounts that have privileged accounts. Those are basically living in a completely separate part of the Active Directory, and they're shielded there. So I can hack that endpoint as much as I want. I'm never going to take over the entire Active Directory by just waiting there for an administrator to log in. Again, it will add percentages to your hacking journey, and they multiply through, right? The EDR slows us down. Yeah.
It's going to be played there.
All right. What else?
Local firewall.
Local firewall is good, sure, yeah. Probably not to prevent the first computer from being infected, but chances are that that person that clicks on a PDF-looking link file inside a zip, that's not your Windows administrator. That's some random person in the organization. And from that computer, you now want to break out and hack other computers, right? So, of course, any kind of network segregation and firewalling helps with containing the hacker. It won't contain forever, right? Those firewalls have holes in them. But, again, it adds percentage points. It adds hours or days to the hacking journey. And that's really your goal here, to drive this up to maybe double the effort ultimately, at which point you're not the most attractive target anymore, for instance, to somebody like a ransomware gang that just wants some quick money, right? I guess I'm just going to continue without slides for now. Last idea, and the one that you should... oh, there we go. Yeah.
Okay.
Why do we need this?
It's here.
Oh. Wait. Oh, I see. Okay.
Almost there.
We basically already went through this entire list. So the one idea that we haven't discussed yet, and if you just want to do one thing to make your organization more secure today, do this thing. Make it harder for the LSS process, that's basically where all the passwords are stored locally, to be dumped. Right? There's a configuration parameter, run as a protected process. For some reason, it's not set by default on Windows versions before Windows 11. Windows 11 made this default. So if you have anything prior to Windows 11 running in your environment, set this parameter today, and the next red teamer is going to hate you for it, right? It really makes their life more difficult, right? Not impossible. None of these make it impossible, but, race with them. All right. To conclude on this part, and then I've one more thing for you all. EDRs are complex solutions, but they overpromise on their capabilities, as we've clearly seen. They do not detect most malware if it is evading with well-documented techniques. We showed nothing that wasn't documented elsewhere today. And as long as they're not using Cobalt Strike. So EDRs are mostly Cobalt Strike detecting tools these days, right? Plus a few heuristics that make the red teamer paranoid in not wanting to touch certain things. And that's exactly why you should use them, right? To make the red teamer paranoid. It's like people putting a security, a plate of a security monitoring company outside of the house without subscribing to that service, right? The thief is paranoid by just seeing that, right? And they'll be much more careful not to trigger any of the alerts that may or may not even be there, right? Okay, so EDRs at 12%, but that's the best case. I have one more thing for you, and that's a few CVEs that dropped today. We looked at another EDR tool. This is not one of the three I mentioned earlier. And we actually found that you can not just circumvent its protection, but that you can use the EDR against the organization, because EDR, again, is complex software, so it too can have software bugs, and if your EDR introduces additional software bugs into the environment, it's doing exactly the opposite of what it's supposed to do, protect you, right? So in this particular tool, we found basically two sets of vulnerabilities. One deals with default credentials. As stupid as that sounds, of course, sure, there's credentials everywhere, and even default credentials in security tools. The other one is more API security. So this solution has default credentials for its management interface. So a lot of these EDR solutions have not just a piece running on endpoint, but a management backend that all the alerts are reported to, but from where you can basically orchestrate your fleet of EDRs. And you see really nice configuration parameters, basically giving the hacker not just the option to switch off all of these things, but also a lot of telemetry about what's happening in the environment. Really a treasure trove of information if you can access it. And yes, it does have a default password, and it wasn't changed everywhere, right? I think that's rectified now. We've been in responsible disclosure with this vendor for some time now, but that's not to say that other vendors don't make the exact same mistakes, right? The other set of problems are more around API security, and again, an authentication issue, or in this case, the complete lack of any type of authentication for things like get all the deception users, get exclusion profiles, get the file monitor, the list of monitored files, right? So again, excellent telemetry for the hacker to know what you should not touch, but also to know what you consider important in your environment, right? So again, those bugs have been fixed. The CVEs were published today, and hopefully all of what we presented today inspires you either as a red teamer to really spend some quality time with EDRs and really learn how they work. It's not that difficult, as I hope we motivated, and you just need it in your tool chain. And as a blue teamer, just be aware that, while EDRs are definitely a must-have tool, they're not a cure-all, and balance it with other controls that you need in parallel, and don't trust the marketing basically around EDR that they solve marketing. With that, thank you very much, and we invite your questions.
Thank you very much, George and Karsten. And apologies for the slides issue there, a bit of a technical glitch. And thank you very much for bearing with us through that. So we've got a few questions up on Slido here. I think the top one there. Is there a decent open source EDR out there available? What would be some challenges in creating one?
You want me to answer that? So EDRs are mostly found in the Windows world, because malware is mostly found in the Windows world, right? The way that Linux systems are abused is not usually through malware. It's definitely not through people downloading zip files with link files and opening PDF. So that's very much a Windows, perhaps Mac world, right? But there is a set of security tools more referred to as host intrusion detection systems. And of course, many of them are open source. Of course, AuditD can basically give you a lot of telemetry. Then there's a software package called Wazoo, W-A-Z-U-H, that uses a lot of that telemetry, and you can do detection rules by just pumping your AuditD information into something like Elasticsearch or Splunk. You can do a lot of analysis there, but it doesn't use any of those behavior analysis techniques we discussed today. I've not seen that in an open source way on Linux, and it would kind of defeat the purpose too. If we knew exactly how an EDR worked, it would be easy to circumvent. So that they have to play a little bit with obscurity to be effective.
Thank you. Moving on to the next one. For the test lab, which I think he showed early on in the environment there, it was mentioned in the slides the upload function is disabled. However, this means missing out analytics functions that the EDR performs in the cloud, which you will not find out until actual usage. How do you overcome this analysis feature on the EDR server side?
Technically, maybe there was a confusion. We are actually using the cloud services of the EDR. We are actually using that information. The only thing we are missing here is that we are not sharing our samples, because that would mean that if it gets compromised once, basically that data is going to be extended to other executions, and we don't want that. That's the only thing we are missing in our test lab. But every capability of the EDR, including the backend and everything all the analysis that the backend is performing, is still there, and we are still considering that for our analysis purposes.
And we should add that that's kind of a standard deployment too. For two reasons, companies don't necessarily upload everything that hits the endpoint, right? One, on the most critical servers, of course, that server is not supposed to communicate with the internet at all. So it doesn't have that direct connectivity. But then, at least in Europe, companies just don't upload everything into some US cloud provider's cloud that hits the endpoint, right? They don't want to, by default, have everything analyzed by another company. Rather, they want the analysis to run within their premises. So, for all of those reasons, we chose to switch off that feature. But yeah, we also wouldn't have measured behavioral analysis. So everything that happens in the cloud, by definition, is not behavioral analysis on your endpoint. It is, again, putting it in a sandbox. And I would make the point that that might actually be the better way to do stuff, because in theory, a sandbox is perfect, as long as we can make sure nobody detects the sandbox, right? If you can enumerate all the abuse ways and avoid all the ways that people find out that they're in a sandbox, this is the way to go. That doesn't need to be complex, possibly buggy software running on everybody's endpoint.
Are there any instances where you cannot obtain an EDR to test against? And if so, how do you approach testing and figure out bypass methods against the EDR?
I mean, technically, that's usually some scenario we can face, right? Like, but what we do, like in this presentation we have faced, embedding the EDR using the most common approach to process injection. But usually what we do in our packers is we build the best thing we can do, and we try to be as stealthy as possible. And that includes, realizing that we are going to face maybe an EDR that we don't know about. So we just try to be as stealthy as possible, and we just try to build the best payload, we could. And hopefully, that lands the user host, and it executes. But you never know. It's always like a game with the EDR in which if you don't have the EDR, you never know if it's really going to bypass it.
Have you played with zip binary file sizes? In my experience, files larger than 50 megabytes can help bypassing with cloud analysis. Is that something you've come across?
I know that sometimes when you use a really heavy process, it can exhaust the resources of the EDR, and then it stops the analysis. But I never try big zip binary files, because mainly you need to download them on the host computer, and usually if they are big, it's going to take time, and the user is probably won't like them. So that's my experience, but I try, and yeah. Thanks.
Any chance for NDR evasion primer for red teamers as the next challenge?
Well, probably not before it becomes relevant. In our work, that has never been relevant, and we're doing dozens of red team exercises against anything, insurance companies, power utilities, telcos. We have never been tripped up by anything NDR, right? So if you're investing money in this area right now, maybe it's to get some compliance check mark or some marketing material that you can hand around in your organization, but don't think that it actually slows down hackers penetrating your network.
That's fairly straightforward. Where would the malicious DLL downloaded from the internet need to reside in order for teams.exe to load it instead of the intended legitimate DLL?
Okay, this is funny, because actually it's kind of stupid that Teams is installed in the local app data folder of your user, which means that basically the user can write there without any administrative permissions. It's not in the program file folder, but it's on local app data. So that's the reason we are able to exploit this path so easily. So it would be local app data, Microsoft Teams current.
But generally speaking, it needs to go either into the Windows system directory where all the DLLs live. That's kind of the default place, or the local directory where Teams lives. That's where we put it, or any directory in the path. Right, so all of them are looked at before Teams gives up and says this DLL doesn't exist.
Have you encountered any effective EDR that was able to detect your attack post-injection based on process memory anomalies?
I mean, in this exact scenario, we didn't, because in our samples, it hasn't happened. But I wouldn't be surprised if it happens. Usually, using these techniques, some EDRs, if you don't build build a different hooking methods, and then you need to overcome them by working in a different way. So I won't be too surprised if this happens, specifically because once you're doing something suspicious and the process and the EDR analyze your memory region, it's going to detect that there's a cobalt strike shellcode there completely unencrypted, unless you perform some memory tricks, but we're not covering them here. And yeah, I won't be too surprised if that happens.
And see, it almost doesn't matter whether or not EDR systems can do this. As long as the red teamer says they could, the red teamer will be more careful when they see an EDR solution. And that's most of the value you'll get out of the EDR. Not the EDR actually doing anything, but them being so obscure about what they do that the red team will be slower, or the real hacker will be slower navigating environment. It's almost scare tactics, but it works, right? As long as they don't tell us what they do, and as long as they keep changing it, we will be much more careful.
Have you seen any EDR that uses good software architecture and segregation techniques that limit the blast radius of a compromise in the EDR itself, a la Postfix?
Not me. Like, I wasn't part of the things that we disclosed today, so I haven't exactly looked at the implications of the EDR compromise. So in my case, not really.
But I think we should mention one thing, that, of course, an EDR would be extremely powerful when run in the kernel rather than in the user space. Remember how all of these unhooking techniques work? You take something that the EDR put there, and you as the virus, you just override it. That's only possible because the EDR doesn't have any special permissions on your system. It's just running as yet another process, right? If you were to put the EDR into the kernel, that wouldn't be possible anymore. It could really learn all of that telemetry with no virus being able to take it away from them. Why don't we put EDRs into the kernel? Exactly for that reason. Exactly because they're not proven security software that we can rely on, but because they're very complex and probably full of software bugs.
And a quick one to finish off. Have you tried your techniques against CrowdStrike Falcon?
I know that it's a good EDR, but I didn't have the opportunity to test it. But based on what I've heard, I know that it performs like, it has good techniques and good memory, like good detection rate. But unfortunately, I wasn't able to test that one.
But we're happy to test it for you if you happen to have a CrowdStrike installation. Yeah.
Perfect. Well, thank you very much for your answers, and please thank you them again.